presenting a lot of different work here. Most of it's experimental since this is a Bruker talk. So, but a lot of this, was done with the help of several students. So they're here. Jack Janik just graduated. Sudeep Saha is still a PhD working on the same topic. And Jack's at SWR right now. But I appreciate all their help. And then also many other students over the years. There's a lot of things that have led to this point. So I appreciate, all their help with everything and the work they've done. So a little bit about Auburn. Auburn University is kind of like the Alabama Tech for the state. And it used to be Alabama Polytechnic University until they changed the name in 1960 to Auburn University. So it is, an engineering school. I just wanted to remind everybody about the Tribology minor that was mentioned before. We also have online graduate certificates. So we have some online master's and PhD level classes you can take. So there's more information here about that. If you have any questions, feel free to contact me. It was also mentioned that I'm now the editor for ASME. So I just want to encourage all the researchers out there to consider submitting their work to the journal. And I also appreciate everybody who is reviewing for the journal. If you'd like to review, you can volunteer as a reviewer. Just contact me, or it's on the website as well. I will point out there's a special issue for electric vehicle tribology that is coming out soon. It's actually being created, so there's kind of a list of the currently accepted papers online right now. We're not taking any new papers right now, but if you're doing work in that area, I encourage you to submit it. So you can go to the website for the journal and find more information about that. All right, so I'm going to talk about electrical tribology today. I'm breaking this up into kind of two areas, but the physics are kind of the same. Physics and the mechanics are the same. You can look at electrical connectors, which is how I got into this area originally. These are contacts that are designed to transmit electricity on purpose, right? So we use connectors in vehicles, trains, in many different places. That's on the left on this slide here. Some of these orange connectors here, these are connectors that are used in hybrid or electric vehicles. So they need to transmit higher amps and voltages than conventional connectors. The other side of it is mechanical contacts where electric current somehow gets across them, but it's not always on purpose, or most of the time it's not. This happens in electric vehicles, also happens in wind turbines, happens in spacecraft. There's many different applications. In plants where you have static electricity that's being generated, the electric current can run across gears and bearings in these applications. But then it's not desired. So first, I'll kind of start with the electrical connectors. I don't know if everybody realizes how much we depend on this, whenever we're connected to a computer, charging our phone, charging an electric vehicle, plugging in computer components, public transit. It's really an integrated part of our lives now. So these are very critical components, but they also have a lot of reliability issues. So we have to be on top of that to make everything run smoothly. A typical connector has a geometry like this, where you have a pin and then a spring that pushes the contacts together. So you have to have a force that presses the surface together to get good metal contact, usually, to transmit electricity. But then more and more recently, we've been using lubricants and coatings to try to improve the tribological performance of these, because fretting wear is very common in electrical connectors due to vibrations. So this was kind of what led to me to the topic I'll talk about later. But we got into nanoparticle additives for lubricants about 15 years ago or so. And so what's happened here is we work with a chemist at Auburn University who's good at making colloids, or suspended solid particles in oil. I think this is an important part of it because they're stable. If you just sonicate and just disperse particles in oil, they're not stable. So these particles are stable over years. So you have to use a chemical surfactant to do that. So a lot of the stuff I'm presenting today is on silver, but we've also looked at other things like carbon, copper oxide, many other materials. So, but the silver does seem to perform the best for a lot of tribology and electrical conduct. Might not be the best practically because they're a little more expensive, but we've also explored some less expensive options. So initially, when we got into this, first we were looking at tribology or electroconductors, kind of conventional surfaces, not conducting high currents, not really looking at the electrical damage. But I wanted to look at, well, how does nanoparticles, how do they perform compared to ZDDP and other conventional additives for lubricants? So I realize you're probably not going to use ZDDP in a connector, but it's a good comparison to show the difference. So ZDDP, a lot of you know, has been around for a long time. It's a very common, it's mostly for reducing wear, but can help with the friction. You know, it's basically can protect the surfaces by creating a coating. If you didn't know, originally it was designed as an antioxidant and it was kind of discovered by accident. They've been talking about phasing out for decades now because it does have negative effects on catalytic converters. But regardless of that, so the idea was we're going to use this in oil. And if you put this in the oil, what it does is it creates a tribofilm on the surface with a chemical reaction that creates this protective layer, and that can reduce wear. So this is actually a very amplified or magnified picture of an actual ZDP film on a surface. Okay, so it's not my image. So on all my slides, I'll have references at the bottom. Maybe I can share my slides later if you're interested in looking at some of these references. So we're trying to test this in comparison to the nanoparticle additive. And we're using this in a UMT, the older tribal lab by Bruker, okay? So we're running at a constant speed, load, 50 newtons, just a duration of 30 minutes. On this case, there's no significant electrical load. I'm just measuring the electrical resistance across the contact. But here's a little movie showing the test. The holder, there's a ball that's holding onto the beat up part of the metal there. So it's kind of beat up because we use this for a long time. I have some better pictures I'll show you up on the new rig that we've upgraded. But basically this shows you what typical test. So yeah, this test we actually, we don't run at constant load, we're reciprocating. So that's because there's cables attached here that are hardwired. So we wanted to have a hard wire so we get a good signal, because if you don't have hard wiring, you add a lot of noise into your electrical signal. So, but anyway, we're trying different lubricants here. And these are some of the results. So the silver and the ZDP both drastically reduced the friction. We just use pure oil. Here we just use dodecane. It's just kind of a more purified oil, hydrocarbon. And then we also looked at the wear, and both of them reduced the wear. So the ZDP actually reduced the wear a little more, which is kind of expected. Some of these nanoparticles actually can have a slight polishing effect, but you can see in both cases it's drastically reduced for both these additives. The big difference comes in later on. So if you look at nanoparticles, there's a lot of literature. You know, these have been around for 25, 30 years, and